I think we all know what eigenvalue equation is. What is eigenvalue equation? A psi, it's psi, there is nothing to be shy about wave function, it is psi, psi, right. A operating on psi gives you a small a factor multiplied by psi, right. That is eigenvalue equation. What is the meaning of eigen? Yeah, yeah, no, not proper, 1, unique. Eigen actually means unique, so 1, it comes from 1, it is fine, okay. A unique function, unambiguous function, and eigenvalue is unambiguous unique value. So this is how matrix eigenvalue equation is written, right. That was the mistake I made. These lambdas are the same, they will become different, but that is for later, not for now. To start with, the simplest form of matrix eigenvalue equation is Ax equal to lambda x, right. So Arkaprabha was right, lambda is one number for now, it will become many numbers later on, that we will see, right. So this is how it happens. This column matrix is the eigenvector and the lambda is called the eigenvalue, okay, for the matrix, the square matrix, which is n by n, okay, fine. Now what we do is we can write it very simply as a set of simultaneous equations, everybody knows this, and if this is the matrix, what will be the simultaneous equation, what will be the first one? A11 x1 plus A12 x2 plus etc plus A1n xn is equal to lambda x1, and the second one will be A21 x1 plus A22 x2 plus so on and so forth equal to lambda equal to x2, right, and that is how you get the n number of simultaneous equations, alright. These are the simultaneous equations for you, right. This is also Ax equal to lambda x. Now if we take the, if I make the right hand side 0, take lambda x terms to the left, then what will the equations become? What will the first one become? A11 minus lambda whole thing into x1 plus A12 minus lambda whole thing into x2, no, then I am talking about the first equation now. Where did A22 come from? So A11 minus lambda whole thing into x1 plus A12 minus nothing into x2 plus A13 into x3 so on and so forth plus A1n xn equal to 0, okay. The only term that will get affected is the term in x1, right. This is going to be the first equation. What will the second equation be? A21 x1 plus A22 minus lambda into x2 plus so on and so forth. This is what it is. So what we see is something minus lambda term comes along the diagonal, right. So you can write as many equations as you want, and when you get tired you put dots and write the nth equation, okay. So this is a set of simultaneous equations for you, okay. Now if I want to write this modified equation in matrix form, I think you agree with me that this is going to be the matrix, very simple, right, and this is the kind of matrix that actually occurs in many places in quantum chemistry. Whoever has studied 4 to 5 might remember, whoever is studying 4 to 5 now will come across it in a few weeks time, right. So this is the matrix, the first 1 element is A11 minus lambda, then A12, A13 etc up to A1n, then A21, then A22 minus lambda, then what? What is the third one? No, in this second row, A23 or A32? A23, right, then up to A2n, and then you can write the whole thing. So this is your matrix, fine. Now once you have this equation, then you want to get the solutions. What will be the trivial solution of this equation? x, the matrix X is equal to 0, right, that is a trivial solution. What will be the non-trivial solution? That you cannot invert the matrix, right. If X is not 0, but still you get 0, what does it mean? Yes, the non-trivial solution is that this determinant is equal to 0 and this is called the secular determinant, right. So, once again we are going to encounter this secular determinant later on in this course also. As you can understand that if you have if n is significantly large, then it is going to be a big determinant, right. Nobody wants to work with big determinants. So, what we will see is when we talk about bonding in organic molecules, big ones, well when I say big I mean maybe naphthalene, then you can actually cut the matrix into smaller blocks using symmetry considerations. That is called symmetry factorization of secular equations. So, we are going to do that eventually, right. For now let us just work with this as an abstract determinant, secular determinant, fine. Now see, the secular determinant can be written in an interesting way. So, if I go back to the matrix equation, what I want to do is I want to break down this matrix into two. Will you agree with me that this is how I can write it? First you have the matrix A minus lambda multiplied by unit matrix. Does it not work out? Because all non-zero elements of the unit matrix are 0. What am I saying? All off diagonal elements of the unit matrix are 0. Man, sometimes you can say very strange things. All off diagonal elements are 0, so only the diagonal elements are going to have that minus lambda term. Okay. So, I can write it in this fashion. I can call it A minus lambda E into X equal to 0, alright. So, the non-trivial solution is going to be the determinant of A minus lambda E is equal to 0. So far so good, right. Now see, here is the determinant. This determinant has to be equal to 0 for a non-trivial solution. Can you expand this determinant? Half say yes, half say no. Yeah, any determinant can be expanded, right. If you have the, if you know whatever is there and if you have the patience you can do it. It is just that it is written in a general form. But tell me, if I expand it, how many lambdas are there along the diagonal? N number of lambdas. So what will be the highest order of lambda in that equation? N. So it will be a polynomial in lambda where the highest order is going to be n, right. So you are going to get an equation that will look something like this: lambda to the power n plus alpha 1 lambda to the power n minus 1 plus alpha 2 into lambda to the power n minus 2, so on and so forth. I do not know why I was so enthusiastic that I wrote so many terms, but anyway, finally you get second last term. I want to write alpha n minus 1th alpha multiplied by lambda plus you get alpha n. Okay. As a special case, one or more of these terms may be 0, that is a different issue. This is a general equation, right. This is called the characteristic equation of the matrix A. Alright. See, what have we specified so far? When I write this equation, what are the only quantities that can be specified? This A11, A12, A1n, etc. Lambda is a variable, right. I am trying to find the value of lambda. I do not know what it is. Do I have x1, x2, etc. here anywhere? No. The only thing I have is the matrix A. So these solutions for lambda that I will get will be characteristic of the matrix A, the square matrix, n by n matrix A, alright. How many roots will be there? N number of solutions, n number of roots, lambda 1, lambda 2, lambda 3, etc., etc., lambda I, then again up to lambda n, right. So here you see we are going to get many values of lambda, n values of lambda where n is the order of the matrix. Okay. There will be a total of n number of eigenvalues. sometimes they can be equal to each other, that is a different issue, but nominally it is n number of eigenvalues, and these n number of eigenvalues are said to span what is called the eigenvalue spectrum. Okay, eigenvalue spectrum. What does this mean? Can you take this story a little further by yourself? I have a square matrix, n by n square matrix. What I am saying is that if I know the elements of the matrix, then I can write down the characteristic equation of the matrix, and we are going to do that in a few minutes. And then from that characteristic equation I am going to get n values of lambda. What is lambda? Eigenvalue. So a n by n matrix is going to have n number of eigenvalues. Can you say something more now? Something that I have not said yet? What is the next step? Allowed transition comes much later. Just because you see spectrum, you should not think of allowed transitions yet. Allowed transition will come after midsem. Say I made a statement about eigenvalues. Can I make a statement about eigenvectors now? What is the statement I can make? So I should have n number of eigenvectors also, isn't it? I should have n number of eigenvectors as well. N number of eigenvalues means n number of eigenvectors. So now we need to modify this matrix eigenvalue equation a little bit to accommodate for the fact that you can have n number of eigenvalues and n number of eigenvectors, right. This is what we had written earlier. Now what we have found is that lambda is characterized by I, so I can go from 1 to n. So if I write I as a subscript of lambda, I should write I as a subscript of x also, right, but then at the same time I should not lose this 1, 2, 3 all these things, so it should come as a second subscript. Okay. What do you have in any one eigenvector? You have n number of x's, right. So number of those x's go from x1, x2, x3, x4, so on and so forth up to xn, right. But then that is only one eigenvector. What I am saying is I can have n number of such eigenvectors also. So I need a second quantum number, if you want to call it that. I need a second identifier as well, right. So this, for example, if I equal to 3, then this one is going to be the second x of the third eigenvector. The first subscript talks about the rank of x within the eigenvector itself. The second subscript tells us about what is the rank of the eigenvector as such, what is the roll number of the eigenvector. Make sense? Do we agree that we need a second subscript for the x's, for the matrix element? This is your matrix eigenvalue equation, right. Okay. What is I? This is I. This is where I have written I. What does I stand for? I stands for which eigenvalue it is. So you agree with me that there are n number of eigenvalues. Corresponding to each, should I not have an eigenvector? A unique value is associated with a unique vector. Eigen means 1, right. So for eigenvalue number 1, I should have eigenvector number 1 also, right. Wait. So that is why what I do is, instead of writing just lambda, I write I. That far I think we are all on the same page. Now what I am saying is, the moment I write I, it is not sufficient to write only x1 and x2, because x1 for lambda 1 is not going to be the same as x1 for say lambda 3. That is why you need to use a second subscript. So first subscript tells you which row in the eigenvector your x is. The second value tells you which eigenvector it is. So if you just go down, you see what is changing. 1, 2, 3, 4 up to n, the first one is changing. Is the second number changing? Second number is I all the way, isn't it? So that is the identifier of the eigenvector itself. It is like a roll number. What is your roll number? Two 2014, then let us say 003 5104, something like that. So 2014 is a year. So for entire population of people who have joined in 2014, that 2014 is going to remain the same, right? And then 03 is Department of Chemistry. So that is going to be the same for all students of Department of Chemistry, but it is going to be 05 for electrical engineering. And then depending on whether you are a PhD student or integrated MSc student or 2-year MSc student, the next number will change, right? So, you have different levels of identifying. These are identifiers. So, we need the second identifier because we are going to have n number of eigenvectors also. Ziva.
Are you saying that the x1i goes on for I equal to 1 to n?
Yes.
So those have lambda 1, lambda 2 and so on till lambda n, right?
I equal to 1 is associated with lambda 1, one number. I equal to 5 is associated with lambda 5. But what I am trying to say now is that, so now if I put in the i's, then ax equal to lambda x also is not sufficient. I should bring in I there as well, right? And this is how it is written. Axi equal to lambda I into xi. What is A? A is that square matrix that we are dealing with. What is xi? Xi is the ith eigenvector, the ith x matrix, right? What is lambda I? It is the ith eigenvalue. Ziva, does that help understand a little bit? Okay, no, we will work it out together, wait. We are going to actually work out the eigenvectors today. Fine. So now see, for the different values of I am going to get these different eigenvectors, x11, x21, xn1 up to xn1, then x12, x22 up to xn2 and so on and so forth. Last one will be x1n, x2n, xnn. These are the n eigenvectors. Now is it a little clearer? Right? I have forgotten your name, Apurva. No, what's your name? Shubhangi. Is this okay? Fine. So now since it is clear, let us make it turbid once again. Otherwise, there is no fun. Right? Now, what I want to do is this. What do I have now? I have n number of equations. If I write it like axi equal to lambda I xi, then for I equal to 1 to n, for each value of I there is one equation. Who is going to handle so many equations? Is it possible to condense everything into one equation? Is it possible to condense the n number of eigenvalue equations that we have written into one equation? How do I do it now? And without losing the information that there are n number of eigenvectors, n number of eigenvalues. How do I do it? What did you do earlier? You had n number of simultaneous equations. Using matrices, you converted that to one equation. Now what I am doing is, now I am combining the n columns into one matrix, right? That is why square matrix works beautifully. If it was not square, it would have been problematic. You can always multiply an n by n matrix by another n by n matrix, can't you? That is why it is possible to just write the columns one after the other and construct a n by n matrix. Do you know what the solutions will be? Solutions also are not very difficult to understand, because after all, if you neglect everything 1, 2 and all that, if you look at only the first column, that is the first eigenvector, right? So what should the first column in this matrix be? Lambda 1 multiplied by the first eigenvector. Okay, are we all okay with this? So this is my first column, lambda 1 x11, then second row is lambda 1 x21 and so on and so forth until the last one is lambda 1 xn1. Lambda 1 remains the same, it's just a matrix eigenvalue equation. Similarly, the second column will be analogous to the second eigenvalue equation, and so on and so forth until the nth column. Alright. So, what I have been able to do is that I have been able to take those n number of equations and combine them into a single matrix equation, right, clear. So, if it is clear, then again try to make it turbid. Let us do it like this. I multiplied two matrices, fine, and I have got one matrix. Now, I want to see whether I can write this product matrix as a different product, then it will be fun. Let us say this matrix, we know what the name is, right, it is A. Now, the second matrix, what was I calling the second matrix, the eigenvectors, x, right, small x, right. Now, instead of small x, let me write big X, because this matrix is bigger than the constituent matrices. So, instead of small x, write big X, okay. What is the right hand side? So, left hand side is very nice, Ax. Right hand side, what I want to do is, I want to split this as a product of two matrices, and I want one of those matrices to be x. Okay, I have given you half the answer. First one is x. What will the second matrix be? Row vector? In one row? Okay, let us see what happens. This is first row, multiplied with first column, first one by one element will be lambda 1 x1 1, fine. What will be the second one? Do you get lambda 1 x2 1? So, I think we got the right answer the first time. This is what it is going to be. It is going to be the lambda matrix, a diagonal matrix where the diagonal element is the different lambdas and off diagonal elements are all 0. Just multiply and see for yourself whether it works. It works, right. So, this is your lambda matrix, Ax equal to x lambda. Okay. So, now I have taken care of the fact that there are n number of eigenvalues, I have taken care of the fact that there are n number of eigenvectors, and I have been able to combine everything into a single equation and write very simply Ax equal to x lambda, and do not forget that A, x and lambda are all matrices and they are all n by n square matrices. Okay, we like to work with square matrices all the time because they are very easy to handle. Okay, fine. Now, let us see if we can make it a little more simpler. I have Ax equal to x lambda. So, see, if I left multiply by x inverse, what will happen? On right hand side I will have only lambda. What will I have on the left hand side? I will have the similarity transformation, which is also nice, right. So, let us do that. Are you okay with this? We write Ax equal to x lambda. Then I left multiply both sides by x inverse. And of course, with what you will multiply, whether you left multiply or right multiply is all a matter of intuition. You can see very easily that if you left multiply by x inverse, then the right hand side x inverse x gives you unit matrix. Okay, so it will be a little simpler. And when you do that very nicely, left hand side becomes the similarity transformation of A with x. So, see, now we are inching closer to figuring out what actually the values of lambda or x are. In any case, I would better know what A is. If I do not know what is A, then what am I talking about? So, if I know A and if I know the eigenvector matrix, then I can perform a similarity transformation of A using the eigenvector matrix and get all the lambda values in one shot, right. What is this process called? Diagonalization. Starting with a non-diagonal matrix, I have found a way of getting a diagonal matrix by similarity transformation. Moreover, what the diagonal matrix gives us is that it gives us all the n values of lambda at one shot, isn't it? lambda 1, lambda 2, etc. up to lambda n. If I know A and if I know x, as we will see, actually it works the other way around. We actually determine lambda first and then we try to find x.